set up. Let's see if we got anybody here. Oh, we do have some people here. Hello. Let me get set up real quick. I'm not fully set up. Okay. So let me show you the browser before I do anything else. And we'll talk about where we're at. And I'll try to encourage some questions. I see a little bit of lag, so hopefully that's only my local experience and not your experience. Let me refresh. Okay. Okay, so where we're at here, if I go to the schedule, so we're 2 weeks out from the third project, so just a heads up that I'm gonna I'll be answering questions about it, but I will also try to sort of I gave you a little bit of a kickstart last week. If you haven't watched those videos, then you can, where I um, introduced the doubly linked list and what the class and the node inside of it would look like. So this week I'll go through at least one important algorithm for the doubly linked list, if not a second one, and wait for your questions. This week we're doing templates, and for the project, template is important because the project requires, I believe, that you make a template. Yes, so in the project you are supposed to make a templated doubly linked list. So the lab this week is meant to help you along those lines. If we were in class together, I would introduce the concept of stacks and queues. If we have time, I will do that, but I'm going to focus on helping you get the core work started and or completed. So lab 12 introduces no new algorithms. It's the singly linked list class with the change having been made to it to turn it into a template. So I'm going to zoom this one tick and just show you that now there's this new thing at the top of it that says template type name T. It's the same algorithms, but I'm going to talk today about what is a template, how do you make a template, why do we use templates. It's an important concept in C++. You've actually used a template before. If you've used a vector, and a vector is a templated class. So anyway, that's the plan, is to explain to you the basics of templates and how you make one, so that you can do that on the third project, and then talk a bit about at least one of the core algorithms for the third project. Okay, so let me get some stuff for myself. I will do I'm going to make a folder for this. Today's April 21st. Okay, so we've been creating classes up to this point, and most recently linked lists with nodes. But if we let's just look at a class that I'll call box, and then I'll put something inside of it. Don't really care about the public interface just yet, but in the private, let's just say that there's int contents. Okay, so the way we've been writing code so far, if I make a box, by the way, that's a static box, which means that it is created and destroyed automatically for me when it comes into existence and when it passes out of scope. It's created and then destroyed. This B has contents, which you can see, and the contents are an integer. And no matter how many boxes I make, they're all of them are going to have contents that are integers, and that's just fine. But let's say that I get into another application where now I want the contents to be a string. So and in fact, let's call this like int box 1 and int box 2 and int box 3. Okay, and so that's fine. It's a box and it has functions in it, and I can make a box, and they all have integers for contents. But now what happens if I have a new application and I need these to be strings? Well, one thing I could do is I could change the box class so that the contents are now a string, and then I could change my instances so that the kind of just the names match what they are. They're now all string boxes, and that's just fine. Um, but now what happens if I have an application where I want both string boxes and int boxes? Well, I can't use this box because it's strings if I need boxes for both integers and strings. So the one technique you can use, and by the way, this is the way that it would be done in Go, I could make the class. I could make two classes. I could have an int box, and then I could make instances of int box. And I could also make a class string box. And then I could have the contents of those be strings. So now I can make these other instances of string box. So that's one way to handle that problem, is if I kind of want all the box behaviors but different kinds of contents, one thing I could do is simply make two different classes. And this is exactly how I would do it in Go, by the way. I'd create two different structs in Go, uh, one with integer and one with string. Um, so that's one way to handle it. But then if you look at something like the linked list that we've been making, so we have this complex linked list, and the problem right now is that the linked list, the nodes can only hold integers. So the nodes only hold integers. So in theory, if I had this program, then I could make a bunch of S lists. Knowing that I can only use those to store singly linked lists whose nodes contain integers. Okay, so how do I fix that? Well, one thing I could do is I could copy all this stuff, and then I could save this as my string slist. And then change this int value to be string value, and then change this int new value to be string new value. Then change this front to be string front, and then this push front to be string value. I'm not asking you or telling you that you should do any of these things. I'm just pointing out like this would be the process. My S list is integer nodes, but what if I wanted string holding nodes? Well, I could copy all that code and then I could update the implementation uh, being very careful everywhere to make sure that I'm getting strings where I need them. And then I would take the .cpp file, I'd copy that, I'd call that string slist.cpp, and then I'd go in there and I would update all this implementation to make sure that I've got string everywhere. String. And now I have a new string slist class. And then I could make string slists. I think I forgot to change the class name. String slist. I'm sort of going the long way around this just so you have some time to absorb the idea. And now in string slist dot, I'm just going to have to look for everywhere I find slist, change it to be string slist. Okay, so now in my program I can include the string form, and then I could make a bunch of instances. So now I have the ability to do strings or integers because I have two different classes, one that specializes in integers and the other that specializes in strings. And you can imagine if I needed to do floats this way, then I would make a brand new singly linked list um, with to contain floats, and it would have the .h and the .cpp, and I would update it to say float slist. And every time I had a new kind of data that I wanted to store in my ever more sophisticated singly linked list, then I could make copies of that file and then make alterations to them to match the new kinds of data that I want to store in a node. And in the Go language, that's largely the way that would be done, although not 100% of the time. But in C++, there's a mechanism called a template that is designed to solve that entire problem. So I'm going to go solve this problem as a template. So the idea of a template is that you can, in some languages call them generics, but the idea is that you can take the piece of data that you want to be able to swap out at will, and you can template it or turn it into a generic, and then you can use your list for anything that you want. So I'll go through the process of doing that. So I'm going to say, since C++ lets me make templates, I'm not going to make a big mess and make all kinds of different lists. So what I want, and I'm just going to simplify this to have one of each, what I want is to make an slist for integers and an slist for string, and somehow use one piece of code with all of my elaborate algorithms for both problems. All right, so how do we do that? Okay, so here's how I do it, and here's how you're going to see it done in the lab. I'm going to take I'll call this this is lab 12 we're doing. So this is how you would derive it without my help, without the starter code. So what I want is I want to change this slist so that the value inside of the node can be anything. Doesn't just have to be integers. So the way you do that is, the way we're going to do it is we're going to turn the whole class into a template. This T for type name, the T is the way that we're going to refer to the now genericized piece of data. Type name is the C++ keyword. You can also put class here instead if you want, but I find that confusing. So I'm going to template the entire class. And you start by putting this line of code above the class, template type name T. So what I'm saying here is everywhere where the data that I want to be able to swap out is referenced, I'm going to reference it with T as its type name. And some languages call this a generic. So I'll go through the process and show you what that looks like. Um, the other thing, well, I'll come back to this in a second. Okay, so T. So where the data goes in a singly linked list is into the node, and it's right here. It's this value in a node. So I don't want it to be an integer anymore. I want it to be generic. So I'm going to call it a T. So now value is a T. It's an unknown data type. It's some type name that I'm going to refer to as T. I'm also going to refer to new value as a T because I don't know what kind of data that is anymore. It's just some templated type, some generic type called T, but whatever it is, it has to be the same kind of T. So let me show you how this works on the other side before we finish this thought. So the whole idea of templates is I can take a data structure and I can make a piece of data, one or more pieces of data in it, generic. And what I want to do in a singly linked list and then also in a doubly linked list is I want to make the data in the node be generic or templated. So on the driver side, here's what that looks like. So now I have my slist.h. Here's how the template comes into play. You've seen this with vectors. So I can specify for every one of my lists what to use for T. So if I want integers, I can say, well, the T for int list 1 is integers. So now everywhere for this list, there's a T, it means integer. But for this list, I wanted string, so I'm going to use for the T's here, string. So now in this instance of the singly linked list, everywhere there's a T, it means string. And I can do this for any type of data. I can use doubles, I can do bools. I can even template my own types. I can pass that in as a T. And the neat thing about this is that I only need one piece of slist code with the type name T in it, and now I can make slist for any kind of data that I want with one piece of slist code, which is quite good. Let's finish the thought here. So I start with the actual piece of data that I want to make generic, and that's the node's value. I want the nodes to be able to hold any kind of data. So now I need to be careful and go and genericize every appearance. I didn't want to put that there. That's all right. Let me just move this real quick. Okay. Everywhere where I'm referencing the node's data type, I want to use the generic reference to it called T, an unknown data type. So I'll just go back to the top. Here's one. When I push front, I don't know what kind of data it is for any individual list, so I will just use the type name T. So for my string list, that T is going to be a string. For my double list, that T is going to be a double. For my beverage list, that T is going to be a beverage, and the compiler just takes care of that. Here's another reference. When I get the piece of data from the front node, I don't know it's always going to be an int. It's going to be some generic unknown type. Size doesn't change. Whether or not it's empty doesn't change. Clearing it doesn't change. Converting it to string doesn't change. So that's step one, is to create a template. And we're going to do a doubly linked list today, and I'll give you one algorithm. To create a template, you put template type name T, and then you go and you hunt down all the references to the piece of data that you now mean to be genericized or templated. Okay, I like the word generics, which is what a lot of languages call it, better than template. Okay, so part two of this is I have just found that it's easier to manage templates and compiling them, they are kind of a funny thing to compile, um, unless you do this little trick, and then they're not hard to compile at all. So we're going to kind of break a rule, but do something that you've seen before. When you do a templated class, what I recommend is that you make it as an HPP. So I'm going to call this slist.hpp, and what that means, what I'm communicating with that extension, is that I mean for this to be an all-in-one header. So it has the headers and the implementation all in one place. And for templates, I literally mean let me go grab it real quick. I literally mean to grab the implementations. So I'm in the .cpp file from last week. I'm going to grab the implementation and I'm going to put it in the header file. So notice, by the way, I am inside of the class. And for my course, this is how we do templates. We're going to have templates are one file. They're a .hpp file. There are no separate function headers. They are just headers and implementation all at once. So this is the first time that the constructor has been announced or declared, and it's also going to be implemented right there on the spot. So we're going to end up with one file, an HPP file. In my driver, I'll finish this in a second, but in my driver, that means that I'm going to include HPP, not .h. And the other thing that I've been saying over and over and over again is that you don't actually compile HPP files. So this newly templated singly linked list will never be compiled. It will be included. That's how it gets in. So your templates, at least for me in my class, get into your program by being included in the places where you use them. Anyway, then you just go down and you just take all your implementations. So here's the destructor. And right here for the HPP file, right there on the spot, I'm going to declare it and implement it. And I'm going to do that for all of them. I'm not actually going to finish this thought, but hopefully you get the idea. There's push front, and then you do all of them like that. So this file is going to be big and unwieldy because it's going to have all of its code in here, but it's way easier to deal with templates this way. They don't compile in the typical way that you're used to because of this funny generics stuff, this template stuff. So one file for a template, a HPP file. It has the template line in it. It has the class. And inside of the class are all of the functions and their implementations all in one place. That's how we're going to do it in my class. So that's what you're seeing on this week's project. I'll go look. Can you see the browser right now? You cannot. So let me bring up the browser and just show you. So notice on this week's lab, there's no header and implementation file. There's one file, and if you look at the file, it is called slist.hpp. So that's me telling you everything goes in here, everything. And notice I've even sort of set it up for you to fill in the blanks with. So here's the constructor, and I left it empty for you to fill in. Here's the template line, here's the class line, here's the function, left blank for you to fill in. You've already got all this code. So your job basically this week, oh, the node is incomplete because I wanted you to have to contend with the template stuff, which I just did. Showed you how to do that. But notice in some places, like push front, I already did the T for you, and in front, I already did the T for you. So hopefully that makes some kind of sense before I sort of push on and do something for the project. I'm getting I have to refresh because I get a Twitch looks funny. So that's all Lab 12 is. You don't actually write any new code. Your job on Lab 12 is simply to uh, acquaint yourself with the way templates are put together. You're taking your same singly linked list code from the last two labs and you are transforming that code into a templated singly linked list class. Uh, and then running it against unit tests to make sure that the template still works. If you look at the unit test, by the way, you'll see how that's changed because now the thing has to be templated. So for example, this first section um, is using the template to create a list of bool. The second section is using the template to create a list of integer. The third section makes a list of string, and that should just happen sort of auto-magically because you have implemented a templated list class with the generic type T, so any data type should work the same. Down at the bottom, there's one with unsigned int templated in. So Lab 12 is, in theory, very easy as long as you understand how the pieces are supposed to be put together. And the reason for that is because then you are left with some space in your head to work on the third project. So I'm going to set up the class part. In fact, what I'm going to do is recommend to you one way that you might set up the lab. So let me, yeah, I want to get rid of, wait, what's this? Yeah, let me get rid of that and get a fresh one. Okay, so a project 3 folder, what I think it should have in it, I'm going to start with an empty one and just begin to populate it with stuff. What I think it should have in it, nope. Um, you're going to need a doubly linked list class as a template, so a dlist.hpp. I'm not sure how tiny that is over there, but maybe you can, I don't know if I can bump the size of that up. But anyway, you need a driver .cpp, which you might call project 3 if you want to. I'm going to call it a driver. You need a file that has main in it. You need a file that has your data structure in it. And then you're going to need an input file, which for now I'm just going to call input.txt. Where to get the input. Where to get the input is from the project. So let me go back. Project 3 has a sample input file. So I recommend that you have that sample input file as your input.txt, and then you develop your first version of your code around it and see if you can get it working. So this is the 3 files I have. I would plus a make file, of course. That should be everything that you need to develop this project. When you submit it, you don't need to submit the input because I'm going to use different inputs to test that your code is battle hardened. But you are going to need an input file here so that you can test it out. Okay, so what does the driver have in it? It's going to have an include for the the data structure, um, plus includes for library stuff like fstream, iostream, etc., string, whatever it is you're going to need. This is going to have main in it. With the argc, argv setup like you've done before. Um, I would probably break this out into helper functions. It's a lot easier, in my opinion, to develop something that's larger and more complex if you break that thing up into functions. So in main, handle the argc for file name. Open the file if you can. Parse the lines of the file. Open and read. Need a dlist instance somewhere in here. Anyway, so you handle the file name coming in like we've done before. You open and read the file like we've done before. You're going to need an instance, or you're going to need a dlist in some form or another. I'll leave that for you. You need to start working that out. Because the whole point of this program is to take commands from a file and apply those commands to a doubly linked list. Oh, add something to the front of a doubly linked list. That's the command, so I will take my doubly linked list and add something to the front. That kind of thing. So as you're parsing the lines of the file, you're supposed to operate on the commands. Make changes to the dlist as per the commands. That's mostly it. That's what the driver does. It handles all of the part that's not the data structure itself. Okay, so dlist.hpp. It's a template, so you need that. You may need includes. So I'll just leave a note there that you might. You're making a class that's a doubly linked list this time. And it being an HPP, what you're telling the world is that everything you need is here. You know you're going to want a size, and you're going to need a node. We've done the node before. Doubly linked list, so the doubly linked list keeps a head and a tail. Let's see, a node has it keeps track of the next node down and the previous one closer to the front. Doubly linked list. The value inside, that's a T from the template. We don't know what the node's going to have in it for a data type. It's a T, whatever that is. You have to, just like we often do in programming, you have to deal in abstractions. So this is about as abstract as it gets. Not only do I not know what the value is, I don't even know what the data type is. It's T, whatever that is. Handy to have. A constructor in here that sort of sets everything up real pretty. I should use thises, shouldn't I? Yeah, I'm going to use thises, make this better. So notice there's a T, because I don't know what kind of value it is, but this value, which is a T, equals the value coming in. This next is null pointer. This previous is null pointer, and that's a fully set up node. Probably some people are put off a little bit by that, but um, it simplifies it a little bit in that the struct only exists inside of the list that manages it. That's just how I happen to like to do it. But that part we've looked at before. The only thing I changed is that I am going template right from the start. Um, and what that tells me is that everything goes in here. Everything goes in here. I'm not going to have any separate stuff. Um, guarantee you, by the way, that someone who's not watching this video right now is going to separate the files and then ask me, how do I deal with these files being separated? Um, so anyway, I say that because if you're here watching me, don't you be that person who does that. Do it just like Lab 12. The list structure is one file and everything's in the one file. This is going to need a constructor. And how do we construct? One file, everything's in here. So what does it mean for the list itself? It might be time for me to bring up my picture. Do I have the camera? I do have the camera set up. Aha. Okay, so we're going to do a little bit of doubly linked list stuff for the time we have left. Let me pull that. Sorry about the shade. It's my bedroom, so I don't really have much of a studio to work with, and I'm on a lawn chair. Okay, so a doubly linked list. Here's a singly linked list. When it starts, a doubly linked list is just an extra marker that both point to null to start. So a doubly linked list, the nodes go in two directions and the list keeps track of both ends of itself in a doubly linked list. This way we can move both directions. We can start at the front and move to the back. We can start at the back and move to the front. We get a lot more options with the doubly linked list. The trade-off is that the code is more complicated. And of course, a doubly linked list, just like a singly linked list, has no contents to start, which means it's a size 0 thing. So this head equals null pointer, this tail equals null pointer, and this size is 0. Templated, so everything goes in there. We're going to need a destructor to clean up memory for us at some point. And just like the single linked list, probably what we'll do is we'll create a clearing function for ourselves. Okay, so let me just give you a hint of what all is going to be in here. You're going to have a push front, just like before. You're going to have a pop front, just like before. You're going to have a front, just like before. None of those change, but now you also are going to have a push back that works from the tail end, a pop back that removes the thing at the back end, a back which retrieves the data at the back end. So those are new, but they're not that different. You just have to think from the tail end of the list. You're also going to have an insert, which we don't have this feature on our singly linked list, but the insert is going to allow us to insert data so that we can, if we choose, make the data be sorted. So insert will take our piece of data and it will place it in the appropriate order, in the appropriate place to maintain an appropriate order in the list. So for example, can you still see my drawing? You can. So if I had a list that looks like this, there's a size 2 list. If I were to insert a 15, what I would want if I inserted a 15 is for the 15 to go in between those two so that they would be in order. So that's what the new insert function is going to do, is it's going to allow us to place nodes in between other nodes, or sort of seek out and find the appropriate place to put a node. Um, we're also going to have a remove. So on our singly, the basic functionality is to pop the one off the back or pop the one off the front. What a remove is going to do, it's going to be able to seek a specific piece of data and get it out of there. So like pop front right now would take the 10 off, or pop back would take the 20 off. We'd need the remove to target and get rid of the 15. And that's complicated because there's a lot of links to fix if you remove something from a doubly linked list. That one we're going to talk about next week. But anyway, those are going to be new. We're going to have a toString. We're going to have a getSize. I think that's most of them. I might be forgetting some. We'll go back and review the project here in a bit. But that should be most of the functionality that the doubly linked list wants. These 6 up here are very similar to the singly linked list, except for you have to think that every node now has an additional link that has to be dealt with. So I'm going to give you a starter on one of these. And then on Thursday we'll probably do insert, and then we'll do a remove. We might have I think there's probably a remove all as well. Actually, I don't know that we need that. Oh no, there's a get. There's a get. What get will do is basically locate and retrieve a target piece of data. So front gets the thing at the front, back gets the thing at the back, and get will locate a specific piece of data and retrieve it for you. So that's, I think, most of the function complement. Okay, so we're going to do push front, and then I'll call it a day, barring questions, but let's do a push front on a doubly linked list. So with a T, why a T? Because we have to write this not knowing what the underlying data type is. It shouldn't matter. It is what it is. It's a string, it's an int, it's a bool. It is whatever it is. It doesn't really matter. I'm just going to put it in a node and add it to the list. Okay, but pictures help because you have to keep track of what does the list look like at any given moment. So here's the list to start. Head and tail point to null to start. So if we push something, it's a similar process, but we have to keep track of all of the links. So let's think about the push front in this case. We're going to make a node for it dynamically. When I do that code, what I get is a node constructed whose next, I'm just going to call them N and P. No, I'll write it out. I'm going to get a node whose next and previous are null. And the contents are whatever that value is. I also, by the way, have this N reference pointing to it. So that is what I just wrote. Node star n equals new node. And when I make a new node, the constructor will create a node, put a value in it, and null out the next and the previous pointers. So now what I need to do is hook this thing up. This one takes more work. to sort of consider how does this work. But for now, let's just say that the head equals that n. So we'll take this head and point it here. The tail, here's another pointer. I got to keep track of that stuff. Equals n. And the size grew by 1. So that's the process if I started out with nothing there. But now let's redraw that, and then let's see what happens if we were to add a node in front of that. So now we have a list that looks like this. I can go all the way to the top here. And I'm just going to use 10, 20, 30, 40, and 50 and pretend like those were the values. Gets a lot more stuff to look at, but let's pretend like we put. Okay, so that needs to be pointing at the node. Okay, so head points at this one, tail points at this one. Its own links go nowhere because it has no neighbors to start. So that's what the list would look like after 1. But now let's see what happens if I were to make a new one. And let's just say for argument's sake it has 20 in it. So I have a lot to work out here. I have to figure out if I'm going to push this one on the front, what has to happen? I have to do something with this link because this link is going to have to connect to 10, which would be my new neighbor. I have to do this link off of 10 because it's now the next one in front of it should be the 20. So that's this one's next is 1. This one's previous is 2. And then I have to deal with this head pointer because it needs to move and point at this new one also. So that's a minimum of 3 links. And then I also had the problem of the tail because now I don't want to move it anymore. So that's a lot of stuff to work out. The way I recommend that you do this is connect the new one first. Like get this new one all hooked up before you mess around with head and tail. So head and tail should be last. So let's hook this one up. So ends next should point where head points at. In code, so before I do head and tail, ends next should point at, if we're writing it in code, ends next points at the head. So I took ends next, and by using the assignment, I relocated it to point in the same place where head points to. Now I need to take heads previous, here's head, previous, and point it where end points to. So now I'm going to take heads previous and point it at. So move heads previous, head previous to point at where end points at. So that moves this one to point down here, which is what we want. So that one's fixed. This one I don't need to worry about. Those two are hooked up. So the last problem is to move head to point where end points to. That's this line right here, so I'm already doing that. This tail piece. So if I move tail to 20, that breaks this because tail should stay on 10. So I need to figure out when I should and should not move the tail. There's only one time when I should move the tail, Um, it's when it's not otherwise occupied. So right now the tail is already tracking somebody, and I don't want to break that. But the situation before, where tail was no longer was not presently occupied with keeping track of somebody. So if the tail is not presently tracking a node, then I'll make it track the newly created one, which is what will happen the first node that comes in. Once you get a node in there, then this one can't happen anymore. So I'll go back and I'll draw a picture of that just to remind you. So here's my initial. I'm just going to call them H and T, head and tail. Null. I'll just make a 0. Uh, so if I make a new node, the very first node, I'm going to say nodes next equals head. That's fine. That just means this goes to null, and that's where it already was. Head, uh-oh, now we have a problem with this code, because head previous, there is no head previous. So I can't just do this code whenever I want to. The only time the head has a previous is if there is a head. So what I want you to see me doing here is kind of working this, like I have to devise an algorithm, and then I have to try it with different situations, and then I have to go back and try it with the old situations again. So if head is not null, okay, that'll prevent this from happening. Then I can say this head, alright, so this next points to null, points to where head points to, which is null, that's fine. If head is not null, but head is null, so that won't happen. Now I move head to n. Then I say if the tail is null, which it is, then I point it at n. That's fine. And then I increase the size. So that algorithm in that situation ends up with this, which is what I wanted. Now I got to see if I put something in front of this one. So now I go back yet again to that second situation and say what happens if I make a new one and try to connect it up. Okay, so here's the new node. This node's next equals head, so that's fine. If head is not null, it's not null. Then I can say this head previous equals this guy, so that's going to be fine. Then I move head to be here. That's fine. If tail is null, it's not, so I don't do anything. And then I increase the size so that worked. So these are harder. They take more planning, they take more iterations. Like you try the basics and then you change the situation and then you go back to the earlier situation and walk back through. Do you notice how I did that? I started with nothing in the list, and then I put one thing in the list and added a second thing, and then I wrote the code to fix that. But then I went back and said, okay, does that still work if I start from nothing again? And it didn't. I had to fix something. It's a pain. It doesn't end up with that much code, but it takes planning and it takes work. Okay, that's push front. In theory, what I would challenge you to do, in theory, you should be able to write a clear function, because a clear function you don't really have to be that careful with head and tail and stuff. You just sort of do the same algorithm as you did with the single linked list. So I'd challenge you to do that one. I would also challenge you to do push back, which is going to be something like push front, except for working from the tail end. So you should get it and draw a picture and try to work that out, because it seems like, oh, everywhere there's head. Yeah, that's fine. The videos are posted on YouTube already anyway, so I mean you can keep them for yourself, but they're on YouTube and uh, that's mostly forever. But yeah, yeah, you're free to keep them on your disk if you want. But they are available on YouTube for probably at least a few years from now. Okay, so what you should try to do is adapt push front to make a push back. Um, just work it out. Don't just sort of copy and paste all the heads become tails and all the tails become heads. It's a lot better to work it out because it's really easy to make mistakes if you're not careful. The other thing you should try to do, in my opinion, is front and back. Front is pretty much exactly the same as the singly linked list. Back is an adaptation to work from tail. I'm going to do probably pop back on Thursday. I may also do insert on Thursday, we'll see, but I'll start with pop back on Thursday. Um, you might be able to do the clear function. The string is relatively straightforward. Get size is the same. Get insert and remove, I would argue, are probably the tricky ones here. So um, those are the ones that we'll try to look at together. Yeah, that's my plan. So if you don't do anything else toward the project, which you should do more than just this, but at a bare minimum, while it's fresh in your mind, go have a crack at pushback. You can also, by the way, you can probably adapt some of my unit tests from our recent labs, especially lab 12, to see if your doubly linked list is functioning. Okay, that's it. I will wait for questions, and otherwise I'm done with what I got for the day. All right, we'll be here at 10 a.m. tomorrow for question and answer, and otherwise I'll see you guys on Thursday at 11.